Yes. So can we start, sir?
Yeah,
Okay. So hello all. Welcome to the IIT Gate classes. In this particular session, we are going to cover the GATE 2024 Production and Industrial Engineering solution. And this will be the session for applied mechanics and design. Right. In the section B, we have applied mechanics and design. That portion we are going to cover. First of all, we will look into the weightage, right? Uh, like total number of questions that were asked. So here, if you see, that is a GATE 2024 Production and Industrial Engineering Solutions. And here we are discussing the section B, in which you can see there is applied mechanics and design. That means in this one, we are going to cover strength of material, and then theory of machine and mechanisms, and then engineering mechanics, right? The basic engineering mechanics. Here, if you see the total number of questions in this section, for this particular GATE PI paper, production and industrial engineering paper, the total number of questions that were asked, the count were 6. In that, the 4 questions were there of 1 mark, and the 2 number of questions were there of 2 marks. So total weightage for this section out of 100 marks is what? 8 marks, right? So 8 marks were allotted to this section B. So you can see that there is a small portion they are asking from this section, but the majority will be there from the industrial engineering and production and manufacturing, right? So by looking at the weightage, and if you try to compare with the previous year, so it is almost on a same line. In the previous years also we have the 8 to 10 or 8 to 12 marks, varying for this particular section. Sometime higher weightage, that means more than 10 marks. Otherwise, it will be less than 10 marks, right? Coming to the question number 1 in this applied mechanics and design, there is a MCQ question based on the strength of material. Now, we can read this particular problem here. A uniform cantilever beam of length L, which is having a flexural rigidity EI, and it is loaded by a force F as shown in the figure. Now here they have given the uniform cantilever beam. That means if you take this particular beam as two part here, let's suppose for example if I mark the point A, B, C. So for AB portion and for BC portion, we have the same material, we have the same geometry. That's why we have the same flexural rigidity, guys, EI. Assuming that the Euler-Bernoulli beam theory is applicable here, the magnitude of the static deflection at the free end of the beam is what? Right. So here they are asking what is the deflection at a point C? What is the static deflection at a point C? Now the question uh, is there any difference between the dynamic deflections and static deflections? So here, whatever the load is being applied, it is just applied at the point B. It is not falling from some height or with some velocity, right? It is just acting like a static force F at a point B. So whatever the deflection will be there because of F at a point C will be static deflection, right? But if I take the same beam and if I apply the force F with some height here, that means if I fall, drop some mass with the some kg, with some 20 kg or 30 kg at particular height onto the beam at a point B, then whatever the deflection at point C would have been, that is nothing but dynamic deflections. Again, that is also deflections, but that is the dynamic deflections, right? Now here, and that deflection will be higher than the static deflections, right? So again, this thing we are discussing so that you know uh, that can be the question for next year gate, right? Because that is what the strategy of gate examination who are basically framing the questions. Now by looking at the solutions here, So first we will try to draw the cantilever beam. This is what we have, the cantilever beam. At a point B, we have a force F, A, B, and C. Now, first of all, we will try to see what is the elastic curve, and that elastic curve can only be made, can only be made based on what? Bending moment calculations for each and every portions. If you take a section BC, there is a no bending moment because there is a no force onto the right side. Onto the left side, if you want to see, there is a reaction force. There is a reaction force at RA Y, which is nothing but F, and there is a reaction moment. There is a reaction moment of F into 2L by 3 because the length is what, guys? 2L by 3. And from here, we have the length of L by 3. So that is the reaction moment. And we don't have any horizontal reactions as there is a no horizontal external force. There is a no horizontal external force. So we can see there is a no bending moment in the portion BC, and there is a bending moment in the portion AB, which is nothing but F into X. So if you try to see the Euler's Bernoulli's equations for basically finding the bending for finding the bending moment as well as the deflections, we have what, guys? Or maybe if you see the bending equations, m by I sigma by y, which is equal to E by R, right? So if you try to compare these two terms, the first and third term, m by I, which is equal to E by R. So what is the radius of curvature, guys? EI by m. So for the portion BC, the bending moment is 0. Then what is the radius of curvature for BC? Infinite. Infinite means it's a straight line. And what is the radius of curvature for the portion AB? Again, it is varying. Why it is varying? Because bending moment is varying, right? So it will vary. Some variation will be there, like a parabolic. So if I draw here the elastic curve, so till point B it is like this, and then we have from a point B we have some straight line. So this is what we have, a parabolic variation, for example, and here we have the what, this straight line. Now what is the benefit of drawing this elastic curve? We have the benefit, like we can calculate what is the deflection at a point C. This is what we need to calculate, and that can be easily calculated from the deflection at a point B, and whatever the slope here is there, the same slope will be here also, because at a point B, for a straight line and for a parabolic, they are at the common point. So to have a continuity, they must have the same slope, right? And what is this value? Theta b into this particular length is L by 3. So if you try to see the deflection at a point C, static deflection at a point C will be delta b plus theta b into L by 3. Now what is the delta b? Let me remove this part. Let me remove this part. Yeah. So what is the delta b? Everybody know the standard formula. A cantilever beam which is having a certain length L, for example, a cantilever beam which is having a certain length L, and if it is subjected to a constant force F, then what is the deflection? FLQ over 3EI. If I write here the same thing, the formula will remain same F, but the length is 2L by 3. But the length is 2L by 3. here to here. So it's a 2L by 3 cube over 3EI. So what are the delta B, guys? 8FL cube over 81EI. What is the slope? Slope formula also we have FL square over 2EI. Then F is same, but the length will become 2L by 3 because from a fixed point to the point of application of load, the distance will be L. But here, if you see the fixed point A and the point of application of load B, the distance is what? 2L by 3. So what you can write, guys, here? 4FL square over 2EI into 9. So 2FL square over 9EI. So that is what we have theta B, guys. That is what we have theta B. If you try to put into this formula delta C, which is nothing but delta B, 8FL cube over 81EI. Theta B is what, guys? 2FL square over 9EI into L by 3. 8FL cube over 81EI plus 2FL cube over 27EI. So if we take common, so 81EI will be, LCM of this one. And then if you write numerator, it is 14FL cube, right? And this deflection will be in the downward directions. So that is what we have the answer. That is the deflection at a point C will be 14 FLQ over 81 EI. So which option should be correct? B should be correct, guys. B should be correct. Right? If you have any doubt, let us know. We can discuss few more. No, basically the method to solve this particular problem. Right. So it is a very basic problem which already being asked in mechanical, civil previous years also. But why I have taken this question? No, and initially I have explained regarding the concept of what? Static deflections. Right? Why they mention the term called static. So this is regarding the question number 1. Now moving on to the question number 2, guys. That is nothing but question number 28, and that is multiple select questions. Again, what they are asking for a mild steel specimen. So mild steel is basically what? Being a mechanical engineer, you should know every material, whether it is a ductile material or brittle material. So mild steel is basically what, guys? It is a ductile material. Straight away, you should know ductile materials are very, very weak in shear and strong in tension. Right? Strong in tension. For a mild steel, it is subjected to uniaxial tensile load. Which of the following statement is or are true? Now, try to focus on this question and try to see what they are asking, guys. The first statement, what they have mentioned, the engineering stress strain curve is linear within the elastic limit. Now, when you see the, first of all, we will try to draw the stress versus strain diagram. Again, multiple times in the previous year also, this question they have asked regarding the stress versus strain diagram, right? So first of all, we will try to draw the diagram. Stress versus strain diagram. And if I draw here, Now here if you see and focus your attention, then there is a point O, then there is a point A, there is a point B, there is a point C, there is a point D, there is a point D, E, there is a point F, G. No, there is a specific reason why I have mentioned here few points. Now, what is the point A, guys? The point A is basically a proportionality limit point. Point A is basically a proportionality limit. Proportional limit. That means the curve O to A, the curve O to A will be what, guys? The curve O to A will be the linear curve up to A. So ideally, the Hooke's law should be valid up to this particular point only. Hooke's law should be valid up to this particular point only. So what they have mentioned in the particular statement number 1, the engineering stress strain curve is linear within the elastic limit. See, they are linear up to the point A, but from a point A, beyond the point A, the curve is what? A little bit non-linear. If you try to see the zooming part, it is like this. There is a little variation from a point A to B. It is not a straight line. So what is the point B? That is nothing but elastic limit. Elastic limit. What is the significance of point A? Hooke's law is valid up to this point. Hooke's law is valid up to this point. What is the significance of point B? The significance of point B is that after unloading, after unloading within the point B, entire strain can be relieved. What is the meaning of this? After unloading within the point B, entire strain can be released. There is a no permanent deformations. There will be only elastic deformations and that can be fully recovered till the point B, till point B. What is the point C? The point C is the upper yield point. And the point D is what, guys? The point D is a lower yield point. Which is nothing but design stress for mild steel. What is the point F? Point F is basically a ultimate point, which is nothing but at which the necking will be started taking place. The necking will be started taking place. And what about point Z? The point Z will be the failure of fracture point, at which the material will fail. So this particular graph is nothing but a engineering stress strain curve. What is this graph, guys? It's an engineering sigma or means stress strain curve. Then what about true stress strain for a tensile loading? It will be like this. It will be start deviating from a point here. It will be start deviating something like this. After a point D, the moment plastic deformation will begin, the true stress strain diagram will be start deviating, guys, something like this. Till the point C or B, the true stress strain and the engineering stress strain will be remain same. This is true stress strain curve, right? Please try to draw it. Very, very important, guys. So what they have mentioned in the first statement, the engineering stress strain curve is linear within the elastic limit. Whether this statement is correct or incorrect, definitely this statement is what, guys? Not correct. Definitely this statement is not correct. In a very general sense, we tend to say it is linear up to elastic limit, but that is the approximation. What about the second statement, guys? The specimen fails in a cup and cone type fracture. The specimen will fail. What, guys? The specimen will fail in a cup and cone type fracture. So again, mild steel, it is subjected to what? Tensile loading. In fact, if you see the mild steel material, there is a mild steel component. If I apply the tensile loading, for example, like this, and if I draw the state of stress, it is a uniaxial tensile or uniaxial state of stress conditions. Uniaxial state of stress. And correspondingly, if I draw the Mohr circle, if you draw the Mohr circle, guys, shear stress versus what? Normal stress, then you can see corresponding to this phase, what are the coordinates of A? Sigma comma 0. And what are the coordinates of B? 0 comma 0. So there will be a Mohr circle corresponding to this state of stress will be what? It will be like this. It will be like this. So it is sigma comma 0. It is 0 comma 0. And this will be the center. What is the center of the Mohr circle? Sigma x plus sigma y will be 0. And what is the center, guys? Sigma x is sigma by 2 comma 0. Sigma x is sigma, sigma y is 0. Now you know that the mild steel is basically a ductile material and it is gonna fail by maximum shear stress plane. What are the maximum shear stress plane? CD and CE. These are the maximum shear stress plane and they are there at an angle what, guys? They are there at an angle. One is there at an angle what? 90 degree. One is there at an angle what, guys? 90 degree clockwise. And one is anti-clockwise. In the Mohr circle, if it is there at an angle of 90 degree, then in actual it will be at an angle of what, guys? At an angle of 45 degree. So these are the two planes at which the material will be start failing. So for example, this is a plane. If I consider, and this is there at an angle what, guys? This is there at an angle. For example, this is there at an angle. This is a CE plane. And one plane is there at an angle what, guys? 45 degree but clockwise. 45 degree clockwise. What will be there, guys? This will be the CD plane. Let me rewrite again. This will be the CD plane. This will be the CE plane. So how the failure will be taking place along these two particular planes? It will be like a cup and cone fracture. Let me show you. This will be the cup and cone fracture, guys. You can see that along this plane and along this plane, the failures are taking place, and that they are taking place in the form of what? Cup and cone fracture. This happens when the material, ductile materials, mild steel, if it is subjected to tensile loading. If it is subjected to tensile loading, guys. Right? So any doubt, let us know. So what about this statement B is correct? The specimen fails in a cup and cone type fracture. The true stress is always more than engineering stress at any finite strain. See, It is almost same till the point B, but after that, my dear friend, you can see that beyond the point D, it will be always higher. The true stress will always be higher than the what, guys? The engineering stress, right? So here we have the relationship also. If you try to write true stress, or maybe we can write here. You can just complete this particular part, then we can discuss. So what is the relationship between true stress and engineering stress? All of you might have studied in the metal forming, guys. True stress will be engineering stress 1 plus engineering strain. Engineering strain, right, guys? So for this is valid for tensile loading only. This is valid for tensile loading only. So C statement is also correct. And if you remember, in our daily quizzes, we tend to always say a good numericals, good number of theoretical questions. One of the question, if you see our Telegram group, I have shared one question that the true stress will always be more than engineering stress. That statement is correct or incorrect? That statement is incorrect, because if you see the tensile loading, it will be more, but if you see the compressive loading, it will be less. The true stress will be less. So it should be plus or minus, but for a tensile loading, it is always plus. So you have to read the statement. So B and C both are correct. What about D? The specimen does not regain its original dimension after complete, the specimen does not regain its original dimensions after complete unloading from an initial stress above the yield stress. See, I told you very clearly, till the point B, if you try to unload the material, it will completely regain its original shape and size. That is the elasticity material, quality of the material. But beyond the point C, beyond the point D, if you load it here, right, or maybe if you load it from the initial yield stress, let's say from a point C you are unloading it, then what will happen? Suppose here, then definitely this unloading path will not be remain same, it will be like this. And you can see that this is the what we have, the elastic deformations, and this is what we have, the permanent deformations, and this is what we have, elastic deformation. This much of deformation is relieved, but this much of deformation will be always be there in the material because you have loaded beyond the point C. That is, a permanently strain will be there in the material. That is the unloading path beyond the point C. So again, that statement is also correct. D statement is also correct. So what is the correct option for this? B, C, D. So if you are not aware of this particular graph from a standard reference book, you cannot answer this question. And this year in PI paper, they have asked from this particular curve. In the same aerospace paper, they have asked what, guys? Unloading, loading particular questions. Whatever the point I have mentioned, they have already asked in aerospace paper also. Not only this year, in the previous year, mechanical also in 2015, 18, already they tested the knowledge of stress versus strain diagram. So this is one of the most important part of what strength of material, guys, for all the branches, right? Even in the civil also, they are asking many times a good number of numerical from this. In fact, if they will be asking you what is the permanent strain, what is the elastic strain, in a metal forming, in a production also, good number of numerical can be framed. Right? But if you don't know anything, the minor thing about this particular graph, you cannot answer. Straight away, any person would have answered A, B, C, D. 90% of the students, those who are attending this year GATE PA paper, they will tick A option is also correct. Right. Now, moving on to the next question, guys. Question number 33. In the truss shown in the figure, the member AC Again, this is a question from the trust guys, but little bit of on a slightly higher side, even though it is of 1 marks. Why I will tell you. The member AC is inextensible string. Extensible means it is having a particularly a constant load. Even though any load is acting, there will not be any deformations. Other members are rigid, and ABCD is a square with the each side having a length L, having a length A, not L. The maximum value of the force F for which the truss will remain in static equilibrium. The truss will always be in a static equilibrium. It will not be having any kind of dynamic movement when member AC will not deform. Because see, AB cannot deform, BC cannot deform, CD cannot deform, AD cannot deform because they are rigid. But once the member AC will once the member AC will be deforming, definitely my depend, the whole structure will be start doing the movement. And it will not be remain in a static equilibrium, right? So in that particular case, how to proceed for this numerical? The very first step, what we are observing that there should not be any deformation in the member AC. If there should not be any deformation in the member AC, the force in member AC should be zero. If you see the elasticity concept, delta is what? FL over AE. It is having a length L. It is having a constant cross-sectional area. It is having some elasticity E value. So definitely force in the member AC should be zero, right? If that is a trick you have applied, then definitely you would have got a correct answer for this question. Moving on to the next thing. At a joint P, how many forces are acting, guys? At a point D, at a point B, if you see there is a force 100 kilonewton, and there is a force in the member BC, which will try to push the joint B in these directions, and there is a force, for example, AB. Whenever at any joint, three forces are acting, and when the two forces are acting in the same directions, the force in third member will always be zero. The force in third member will always be zero. The force in third member will always be zero. Similar concept we can apply for a joint D also, but that is of no use. Here the reaction force we can write here dy. Here we have ay ax, but no need to calculate. Directly you can just take the joint C. If you see the joint C, how many forces are acting? The force F is acting at an angle what? 60 degree. Then there is a force BC is acting. What is the value of force BC, guys? If you check the joint B in a static equilibrium, the force BC is also 100 kilonewton. So try to put the values FBC 100 kilonewton. And what about this? What is the force in the member CD? If you take a joint D, there is a dy force, and there is a force CD, and there is a force AD, which is obviously zero. Why it is zero? Whenever at a particular joint, three forces are acting, and the two forces are in parallel or in the same direction, the force in third member will be zero. So what about dy? Dy will be equal to FCD. At a point D, the force CD is acting like this. So here it will be acting like this. This is the force CD, which is equal to dy. Force CD will be acting like this, which is equal to dy. Right, guys? Now apply the Lamis theorem. By Lamis theorem, what you can write, guys? This is the total angle which we have 150 degree. This angle is 90 degree. And what about this angle, guys? This angle will be 120 degree. F angle between the other two forces will be sine 90, 100 kilonewton, and the angle between the two other forces will be sine 150. So if you try to calculate, you are going to get 200 kilonewton as the answer. Try to please note it down. Now, moving on to the next question, guys. So, what is the correct answer for this question? It should be 200 kilonewton. It should be 200 kilonewton. Moving on to the next question, again from the theory of machine and mechanisms. Theory of machine and mechanism. And offset slide crank mechanisms, as shown in the figure. If the length L is 10 centimeter, then the what is the stroke length of this slider they are asking. Already the same question with a different data and with the different final question already being asked in mechanical 2014, right? So this is the repetitive of mechanical questions. This is a repetitive of mechanical question, guys. Now try to understand. So what is the first thing? This is the offset slide crank mechanisms. Offset slide crank mechanisms. Offset slide crank mechanisms. In this offset slide crank mechanism, guys, we have the length L, which is equal to 10 centimeter. What is the stroke length? The distance between the maximum outward stroke and the maximum inward stroke, or top dead center to the bottom dead center. If we try to see the extreme position and the lowest positions, the difference will be what? Is stroke length. Now, how to make this maximum displacement and minimum displacement, guys? By looking at the mechanisms here, there is a crank which is continuously rotating, guys. Now here we have this piston. If we try to see the maximum position, it can go till here. This is the stroke, this is the line of the stroke over which this piston is sliding, guys. So this is the maximum position it can go. This is the maximum position it can go, guys. For example, this is what we have L, and this is 3L. So what is this total L? This will be L plus 3L, 4L. And what could be the minimum position? The minimum position it can go till here. If you try to see the mechanisms, it is like that. And this particular crank is continuously rotating, guys. This crank is continuously rotating like this. So this is the lowest position, this is the maximum position, and the distance between these two will be the stroke length. In mechanical question, they have asked quick return ratio. In that quick return ratio also, you need to calculate stroke length. Or maybe you needed to calculate the angle, right? And what about the offset? What is the offset, guys? The offset, it is given as from the line of stroke to the center of rotations, it is given as L. It is given as L. From here to here, it is given as L. So first of all, we will try to calculate this from here to here. What is the total? Let's say this value is what? Y, and this value is what? X. So what is the stroke length? The stroke length will be Y minus X. What is this angle? This angle will be theta 2. This angle will be theta 1. Right? How to calculate theta 1, guys? So you know that cos theta 1, which is equal to L over what, guys? If you see the triangle O A P, in this triangle, what is the cos theta 1? L over 4L. So theta 1 will be what, guys? The theta 1 will be, if you try to calculate theta 1, so you can keep that value. So it will be 75.522 degree, right, guys? And what about theta 2, guys? cos theta 2, it will be L over 2L. Why it is 2L? See that. What is the value, guys? The total length of the connecting rod is 3L, but what about this distance, guys? From here to here, this particular distance will be 2L only. 3L minus L. It will be what? Overlapping. It will be overlapping, right? So what will be the value, guys? 1 upon 2. When what is the theta 2? It is 60 degree. How to calculate y, guys? Again, try to apply the sine theta 1, which is nothing but y over, or we can apply, let's say, tan theta 1, y over L. Then what is the y? Tan of 75.522. So tan of 75.522, which we can get it as 3.8728 L. What is the x value? X over L. X is what? 1060 into L. What is the 1060, guys? 1.732 L. Now, what is the stroke length? The stroke length will be y minus x, which is nothing but 3.8728 minus 1.732, which you can calculate 2.1408 into L. So what is the stroke length, guys? 2.1408. Length is what they have given in the question, 10 centimeters. So it is 21.40 centimeter. 21.40 centimeter. That is the stroke length, guys. That is the final stroke length, 21.4. That should be the correct answer for this question, right? So already this question been asked in mechanical in 2014. You can refer that. Moving on to the next question, guys. Question number 50. Metallic cylindrical pressure vessel used to store the compressed air in a plant has a mean radius of what, guys? Mean radius of 1 meter. Can we write the diameter? Mean diameter will be 2 meter, which can be written as 2000 mm. What is the thickness? The thickness will be 4 mm. The maximum allowable normal stress is what, guys? 100 megapascal. And maximum shear stress is 40 megapascal. Considering only this data in a design, maximum internal gauge pressure of the compressed air will be what? So before moving on to the next question, before moving on to the solution of this question, if any doubt, let us know, guys, right? So first of all, in a cylindrical pressure vessel, everybody know that there will be longitudinal stress and there is a hoop stress. What are the longitudinal stress? PD over 4T. And what are the hoop stress? PD over 2T, guys. In this one, out of this, what is the maximum value? The maximum value is what? Hoop stress, right? And if you try to see PD over 2T, and if you try to compare this with the maximum allowable normal stress, that means this PD by 2T should be less than or equal to this value. So what should be the P value? Considering the maximum normal stress, what is the D value? D value is 2000 over 2T should be less than or equal to what? Maximum allowable value, which is nothing but 100. What is the P value, guys? It should be less than or equal to 100 into 2 into 4 over 2000. This value should be 0.4 megapascal. Considering the maximum normal stress. But if you consider the maximum shear stress, guys, maximum allowable shear stress, if you consider the maximum allowable shear stress, first of all, calculate the tau max, which is nothing but maximum of sigma 2 minus sigma 3 by 2, sigma 3 minus sigma 1 by 2, like this. What about sigma 1, guys? Sigma 1 is PD by 2T. Sigma 1 is what? Maximum principal stress, PD over 2T. Minimum principal stress, sigma 2 will be PD over 4T. And sigma 3 will be 0. Because we are not considering any radial stress. Then what are the Tom X, guys? Maximum of PD over 40, PD over 80, and then we have PD over 40. So Tom X, which is nothing but PD over 40, should be less than or equal to Tom X allowable. What is the Tom X allowable? 40. So if we try to calculate, this P value should be less than or equal to 40 into 4 into 4 over 2000. It should be what, guys? 40 into 4 into 4 over 2000. It should be less than or equal to what? 0.32 megapascal. By considering the maximum shear stress, the P value should be less than 0.32. But if you consider the maximum normal stress, it should be zero point 0.4 megapascal. Which value should be considered for safe designing so that the material will not fail because of the maximum normal stress or because of the maximum shear stress? It should be lesser of these two values, 0.32 megapascal. If you consider zero point 0.4 megapascal, it may fail early before reaching the zero point 0.4 megapascal because of the maximum shear stress, right? So what should be the correct answer? 0.32 megapascal should be the correct answer, guys. Right? So that is the question number 50, guys. Moving on to the next and the final questions of this session. This question again they have asked from, you can consider like machine design or theory of machine and mechanism. A flat belt drive with a pulley of radius r 20 centimeter is designed to transmit 6.283 kilowatt power at 600 rpm. If the coefficient of static friction between the belt and pulley is zero point 0.3, the minimum value of the tightening force F required to prevent the belt slip will be what, guys? Again, to solve these questions, we need the concept of belt and pulley, right? So if you see the torque which is being transmitted to this pulley, here we have T1, here we have T2, and the power which is being transmitted because of difference of these two tensions, T1 minus T2 into R, which is obviously torque. And how to calculate torque? We know that power formula, power is equal to 2 pi into torque over 60. Now, here we have applied one kind of force F to prevent the slipping. Now, to balance the forces in x direction, F must be equal to T1 plus T2. So before finalizing our answer, we need to calculate T1 and T2. One thing you know, T1 minus T2 into radius is what? 0.2 meter, because radius is what? 20 centimeter. If you convert in meter, it will be 0.2 meter. That is equal to torque. What is the torque value, guys? The torque value is, we don't know. We need to calculate 6.283 into 10 to the power 3 watt, which is equal to 2 pi into n. N is 600 into torque over 60. Then what is the torque value, guys? The torque value will be 6.283 into 1000 into 60 over 2 over pi over 600. You are going to calculate like 99.997 Newton meter. 99.997. So T1 minus T2 would be, you can consider like 499.985. And you know the relationship between T1 and T2 will be what, guys? The relationship between T1 and T2. What is the angle of wrap? Angle of wrap is what, guys? 180 degree. E to the power mu theta. But if you write in a radian, it will be what, guys? It will be pi. 0.3 into pi. So what is the T1 by T2? What is the value, guys, here? e to the power 0.3 into pi, it should be 2 point. This value should be 3.2.566. Remember, theta is what? Angle of wrap. How much of angle both the ropes are making with the pulleys at the center of contact. So T1 is what? 2.566. T2 minus T2, 499.985. Obviously, if you try to calculate, you are going to get 499.985 over that will be 319.2075. What is the T1 value? T1 value will be 2.566 times of that, which is nothing but 819.086. If you try to add, you are going to get T1 plus T2, which is nothing but 819.086 plus 319.2075. If you try to calculate, you are going to get 1138.2938 Newton. If you try to write in kilonewton, you have to divide by 1000, so that will be 1.138, but they are asking round up to two decimal places, so it will be 1.14. That should be the axial force that must be applied, or tightening force that must be applied to prevent the belt slip. Please make a note of it. So that is all about this particular session, in which we have discussed the solution of applied mechanics and design of production and industrial engineering paper. So in this session, in this particular section, I couldn't find any question that need to be challenged. All the question answers are what given perfectly for this paper. If you have any doubt, let us know on our Telegram channel. We will try to resolve it, guys. Right. So for any more information, you can contact us on this number, or you can mail, or you can visit. Thank you all.